Hey, Algebra. Welcome to today's lesson. So we'll start off today with a do now, which is a name I give for the entry task. So if you would please write down the coordinates of point A and point B. You can hit pause until you've got that done. Awesome. So let's take a look at what you got for point A. I count 1, 2, 3, 4 spaces over, 1, 2 spaces up. That would be for +2. Always do the x coordinate first, so that means sideways count first and then up and down. For point B, 1, 2, 3, 4, and then down 2, so it'd be 4, and then -2 because I'm going down. Hey, so there's this third do now question. Here's a graph. Let me explain about the graph, and then the question is down there at the bottom. So every month, your club counts the number of people that attend meetings, and then the graph demonstrates versus how many people there were every month. So the graph's a little bit weird. I don't know what's up with the scale because there's not actually 14 months in a year, but so January would be month one, and so that's here, and then February is month two, and so that's this next dot, and then March, and then April, and so on. Um, so there's a lot of questions that we might ask when we see this graph. What kind of club is it? What's up with the attendance? Why is it okay? But the only thing we're going to focus on right now is, can a month ever have more than one dot? Think about that. You can hit pause until you got an answer written down. Nice. All right. So can a month ever have more than one dot? Um, no, not unless this was a graph that showed like multiple clubs, right? I mean, you have a meeting in January and this is the number of people that came. So there's a dot, right? And the next month, February, you count how many people came and it's this many and there's a dot. If more people come, then the dot's going to be higher up. If less people come, the dot's going to be lower down. But you can't ever have more than one dot. It's like that's how many people there were. So no, one dot per month. Cool. Well, so that brings us to our topic for the day. We're going to learn about functions and our learning target. At the end of this lesson, you will be able to tell what is a function and what is not a function. So we're going to have to get a couple of vocabulary words first. Two vocabulary words. The first one is relation. Relation is an important word in math. It just describes any set of ordered pairs. So set, that's I don't know if it's really a fancy way of saying it, but basically it just means list. And in math, we use this special notation for sets or lists, which is we just put these curly braces around the whole list. So we know everything inside of there is part of the list. So otherwise, you could write down the coordinates of those 2 points from the entry task. The 4, 2 is the blue dot, and 4, -2 is the green one. And you might not know that, oh, those belong together as part of this set, right? You might just think, hey, I don't know, it's those numbers, whatever. Maybe they don't even mean anything. Okay, so it's just a way of communicating to the reader. This is a set. All of that stuff belongs together. Okay, well, there's a lot of different ways that we can represent a relation. So we can list the ordered pairs, just similar to a set. It doesn't communicate to you, the reader, that this is actually part of a set and it belongs together, but it is still a way we can write a relation. So there's just a bunch of coordinates, x coordinate, y coordinate, x coordinate, y coordinate, and so on. We could take those same ordered pairs, and instead of listing them as ordered pairs, we could put them into a table. Maybe this time we actually just started from the list of numbers, and so we could say, you know what, maybe it would be useful to put them onto a graph. Awesome, so we can put it onto a graph. Or maybe we use a thing called a mapping diagram. So a mapping diagram is another way of representing what x coordinates go with each y coordinate. So like from the table, just as a quick explanation, you'd first of all look at what numbers show up in the x column. So there's -2, 0, and 3. -2 shows up twice, but in a mapping diagram, we only list the different numbers that there are. So -2, 0, and 3, those are the different numbers that exist. And then in the y column, we'd look at what are all the numbers that show up there. It's +2, -2, and 1. And so we'd list those in the output bubble. And then the mapping diagram is those arrows. They go from one bubble to the next and show that -2 is the input, or x goes with +2. And then -2 and as an input and -2 as an output. So that'd be this green arrow, and then 0 is matched up with 1, input of 0, output of 1, and 3, 1. Okay, so mapping diagram, if for small groups like this where you've only got 4 different ordered pairs, seems like maybe that's more work. It does communicate some different aspects more easily. You can visually identify what input goes with what output. Um, See that even though there are 4 different ordered pairs, we can see that there are only 3 inputs and only 3 outputs. So we know that some of them are used more than once, and we can see the -2 as an input has 2 different outputs, and we can see also that an input of 1 has 2 different inputs that give that same output. So there's some different features that are more easily accessible just by looking with a mapping diagram. Okay, so definition number 2 is a function. Here's what we're after. This is the point of the lesson. A function is a relation, but it's a special type of relation, not just any relation. It's a relation for which each input, or x value, has exactly one output, or y value. Okay, not more, not less. Every input has one output. Okay, and so if we interpret that, what it tells us is that the x values cannot repeat. You can't use the same x value more than once and have a function. The y values can repeat. That's okay. So if a number of different inputs have the same output, that's fine. That would still be a function. But if one input value has more than one output value, that's not okay. Um, I'll give you an example. Imagine that you have done your homework assignment, you've finished all your math homework, and you want to check your answers with your neighbor, right? And so you say, um, "Hey, buddy, what'd you get for number 4?" And they say, "I got 2." And you're like, "All right, cool, that's what I got." And then like a minute later, you forget that you asked them that, and you say, "Hey, what'd you get on number 4?" And this time, the green one, this time they say, "Oh, I got -2." And you're like, "Well, last time you said it was 2." How do you can't have 2 different answers, right? Question number 4 either has an answer of 2, or question 4 has an answer of -2. You can't have 2 different answers, right? So that's this idea of what is a function. Every input has one output. You don't say, well, question 4 had I got a different answer every time I did it. It's like, well, something is wrong there, right? It's only got one answer. Okay, so the x's cannot repeat. If the x's are repeating, then that means you're getting like different answers every time, and that's not okay. All right, so let's take a look at some examples with using mapping diagrams, and then we'll do some practice identifying what is a function and what is not a function. So here's 4 high schools in our school district: Edmonds, Woodway, Mountlake Terrace, Meadowdale, and Linwood. And in the output bubble over here, I've got their mascots. So if we just match these up, Edmonds Woodway is the Warriors, Mountlake Terrace, of course, were the Hawks, Meadowdale is the Mavericks, and Linwood is the Royals. Okay, so mapping diagram. Each school is matched with one mascot. The fact that the orders don't match is completely irrelevant. I mean, if you're drawing your own mapping diagram, maybe you want, to list them in the same order, which would look nice, sure, but it does not importance mathematically whether the lines cross or not. Okay, what about some college mascots? I don't know if you guys are into college basketball. Here's some college teams. So the inputs, some colleges around the country, and in the output bubble, we got their mascot. So if we match these up, KU, Kansas, it's the Jayhawks. Arizona, University of Arizona Wildcats. Kansas State Wildcats. University of Washington Huskies. Go Dogs! And Central is Wildcats. Okay, so in this case, we got 3 different schools that all have the same mascot, which, like maybe they should have a little bit more originality, come up with their own mascot, maybe. But is this a function? Yes. Every school has only one mascot, right? You don't say, "Hey, what's the mascot for UW?" And you're like, well, it's the Huskies. And they're like, "Hey, what's the mascot for UW?" It's the Bears. Hey, what's the mascot for UW? It's the Lions. You're like, well, no, it's only got one mascot, right? Um, that's what a function is. You ask the same question, you're going to get the same answer every time. Every input's got only one output. Okay. So what if I switch the input and output? So for the inputs, I'm using the mascots, and then for the outputs, we've got the schools. In this case, Wildcats. Let's see, Arizona Wildcats, Kansas State Wildcats, Central Washington Jayhawks are Kansas. The Huskies are UW. Okay, so in this case, I have an input here that goes to three different schools. And that is not okay. This is not a function because that input of Wildcats has, quote, three answers, right? If you say, hey, what's the school that goes with Wildcats? Well, to answer correctly, you'd have to say, well, Wildcats is Arizona, Wildcats is Kansas State, Wildcats is Central Washington. Okay, well, a function only has one input goes to one output, not one input goes to three different outputs. So this is not a function, right? If I compare that to the previous one, every input had one output value. Some of them had the same output, and that is not an important detail for us. Only thing that we're interested in is, does each input go to one output? And it did. All right, so let's move on to graphs. If I want to find out if a graph represents a function, it's still that same definition. Every input has one output value, but on a graph, the input means the x and the output means the y coordinate. So in order for me to find out, does this graph represent a function? Let's just look at one at a time. I like to use a thing called the vertical line test, which is, just use my finger or a pen or a ruler or the edge of a sheet of paper and just move it across the graph. And what I'm looking for is, does that straight line, does my pen or my vertical line ever touch the graph in more than one place at the same time? And this one does. So my vertical line hits the graph, that curve that is on the graph up here, and at the exact same time, it's also hitting the graph down there. Right? This is the same thing we saw in that in the do now. There was a point up here at 4 positive 2 and another one down here at 4 negative 2. This graph does the same thing. So for the input value of this graph is not labeled, but for whatever input value this is, there are two different answers or two different outputs, right? There's a green output and there's a red output. So this is not a function. Functions are super important, not just in algebra, but like just about every advanced math topic after algebra uses this idea of functions, and that is forms the basis of a lot of the more advanced math topics that you'll continue to learn about. So super important. Let's do. Uh, let's do. Shoot, can't grab that line. The next one. Okay, so let's get this line so we can tell the difference between it and the rest of the graph. Okay, it's a little bit thicker than I wanted, but that's okay. All right, so same idea. Vertical line test. I'm just going to take this vertical line and sweep it across the graph. And if my blue vertical line ever touches the graph in more than one place at the same time, then it's not a function. And in this case, it only ever touches once. I mean, if I move it to a different part of the graph, it's going to touch in a different spot, but only one place. It only ever touches one place at a time. Okay, sometimes people say, well, what if you had instead of a vertical line, what if you turned it sideways? And like, well, yeah, then it would hit more than once, but that's not testing whether it's a function or not. That's like something else, right? So the only thing we're ever going to use is a vertical line. It's going to go straight up and down. You move it side to side across the graph. Okay, so this one is a function. All right. Okay, last one. What if you just had a big list of numbers? You have a set, and I want to still ask that same question. Is this a function? Okay, so the most important detail for me to look at, there's like a huge list of numbers, right? I don't want to just like, I don't even know where to start. The most important detail, I'm going to look at the x coordinates. If I ever have the same x coordinate, then that means I need to take a closer look. If I had a different x coordinate every single time, then I don't have to look at anything else. I know it's a function because every input's going to have only one output value. There's no possible way to like say, hey, what'd you get on number four? Oh, I got two. What'd you get on number four? Oh, I got negative two, right? So if that x value does not ever show up more than once, we're fine. In this case, I got three showing up with an output of seven. And then the next time I asked my friend, hey, what'd you get on number three? They said they got an answer of nine. Well, that's not a function. And also, what is up with my friend? He's not very good at math. Maybe I should help him out. Okay. All right. So in closing, let's just try out this mapping diagram. It's an exit ticket. If we were in the classroom, I'd have you write down your answer and turn this in as you leave. But you just hit pause until you got an answer figured out. Is this mapping diagram a function? Okay. And hopefully you already wrote this down at this point. Here's the only thing I need to pay attention to. In this mapping diagram, the input of Huskies goes to two different outputs. And that means suspense. Oh my gosh, this is not a function. All that other stuff that's going on in this mapping diagram with the crossing lines and everything is totally irrelevant. All we're looking for is, does one input have two different arrows coming out of it? All right, good luck. See you guys next